All right, so you've turned in homework 4. I've just handed out homework 5. That's also posted on Blackboard. And that assignment is due on Thursday the 17th. And so you've got a little more than a week there. We have an exam on Friday of next week. And so you'll be turning in this homework at noon on Thursday. That's when I'll have the solution posted, and so that you've got a day to look over the solution before we have our test. And we'll talk more about the exam next week, but if you want to begin preparing for that, one good way to do it is to start learning the applicable terms for the chapters in the book that we've covered so far. So I gave you that list of terminology and vocabulary words that are related to different chapter sections in our book. So that would be one way that you could get an early start in preparing for the test. So today we're going to be talking about evaporation. That's found in chapter 7 of the book. And like I mentioned a moment ago, we're going to have to skip over a couple of slides to try and pack in as much information as possible. Before we get started with evaporation, do you have any schedule or announcement questions that I can answer? All right. Let's watch a video of water evaporating. Have you ever heard the phrase, it's like watching paint dry? Well, we'll watch water dry. That's what we're doing. All right. So this is a time lapse. Let me lower the lights a little so it's easier to see. Okay, so here's a time lapse of water on concrete, and you can see that part of this concrete is in shade and part of it is in the open. So let's watch the time lapse of water evaporating. So the section that had sunshine on it evaporated more quickly than the section that's on the shade. And what we're going to talk about today is the two main factors that drive evaporation. And the first of those is energy, and specifically solar radiation. It's energy that comes in from the sun that provides the energy that's required to go through a phase change. And hopefully phase change is something that you remember back in chemistry. I'm sure you talked about how water is ice, and if you add energy it increases the temperature, and then there's a certain amount of energy required to do the work of going through the change from solid to liquid. And then as a liquid it increases in temperature, and then there's a certain additional amount of energy that's required to get it from a liquid phase into the vapor phase, and then steam itself can also be heated. And so solar radiation is what provides what's called the latent heat of vaporization, and that's how much energy is required to evaporate a certain quantity of water. And what this figure is illustrating is at the top, first of all, what our atmosphere is doing to filter the radiation that comes to the Earth's surface compared to what's coming from the sun. The sun emits a broad spectrum of radiation, including ultraviolet, visible, and infrared radiation. So a wide range of wavelengths, but because of gases in the atmosphere and their ability to absorb certain frequencies of light, only a portion of what's emitted from the sun gets to the Earth's surface. And so you'll notice that some of the gases that are listed here, oxygen, ozone, water, meaning water vapor, carbon dioxide, and so these kind of filter out certain bands and frequencies. And so what comes into the Earth's atmosphere from the sun is generally thought of as shortwave radiation. And then that shortwave radiation is absorbed by the ocean, by the land, by polar ice caps. That energy is absorbed. Some of it's reflected immediately without being absorbed, but that which is absorbed as a shortwave energy, it heats up the temperature, and then it's emitted back outward, meaning towards outer space, as long-wave radiation. So we'll talk about the difference between short-wave and long-wave radiation, and part of what we'll do when we actually get to problem solving and calculations is we have to estimate how much energy is being delivered by the sun to water. This is a conceptual sketch that gives you an idea of the relative quantity of radiation that's coming in to the atmosphere and what happens to it. So you see that if you think about 100 units of solar radiation reaching the upper atmosphere, some of that radiation is going to be reflected back out to space just because it's coming in contact with air particles, and that's causing a reflection. Some of it is reflected by clouds and goes back to space. And the incoming, remember, the incoming radiation is short wave, and so is the outgoing radiation that's reflected. It's only that energy that has been absorbed by a solid or a liquid, meaning like the ocean or soil. Only radiation that's been absorbed is then emitted as long wave radiation. That's where kind of the spectrum and the frequency has shifted, and it's a whole different range of frequencies that the energy is outgoing. But for 100 units of sun that comes in, only about 51 units of that energy is absorbed by the ocean or the land. The rest of it is either absorbed by clouds or reflected by clouds and air or the surface back to space. Incidentally, different color surfaces, as you probably already know, have different characteristics for absorbing or reflecting. So you've maybe noticed before that asphalt feels hotter to bare feet than concrete does because the asphalt's absorbing more of the radiation, concrete is reflecting more of it. In the same way, the polar ice caps reflect more incoming radiation out to space, and when ice caps melt and are replaced by liquid water, or if there is land underneath area that's previously covered by ice, then it absorbs even more radiation, and so there's kind of a feedback loop there. When we lose glacier areas or places that previously were covered by snow, then they heat up at an accelerating rate because more energy is absorbed than it was previously. Now, as a net, if 100 units of solar radiation comes out, you'll notice by adding up all these different components that it's 100 units of energy that's emitted to space. And so the amount of energy that comes in and goes out is the same. And that's kind of, you could think of it similar to the continuity equation that says what comes in must go out unless there's an accumulation. And at least in the short term, there's not an accumulation of energy inside the Earth's atmosphere. Over the longer term, people could argue, that there's global warming, and there definitely is, but we don't see that on the scale of a daily cycle or on the scale of a month. Within the shorter term, there is balance between incoming and outgoing radiation. One of the things that changes how much radiation is observed at a different location on the globe is the area that's projected by the incoming radiation, and they call that angle of incidence. And so if you had a square segment, think of it maybe as a 1 meter by 1 meter square, that the solar rays are coming in, and at the equator that would project approximately a meter of area, because most of the surface of the globe would be parallel to that rectangular surface. But then at the higher latitudes, there is more area over which the incoming radiation is distributed. And so that means that the intensity of light is lower at the upper and lower latitudes on the globe. And this is probably something that you already are familiar with if you've been to a tropical area before, if you've been to Mexico or the Caribbean. Just seems like the sun is more intense there, and in fact it definitely is. I remember being in Kenya at Christmas a few years ago, and it was just absolutely intense. I mean, I got burned even though I had sunblock on in just a few minutes because the solar radiation was so much more intense than I was used to at the upper latitudes in North America. So this is one of the things that you can see reflected when you have observed radiation data. There's a variety of sources, and in the homework assignment you're going to have to look up some of the measured solar radiation to do one of the problems. And one of the things that affects how much radiation there is to drive evaporation is your location on the globe. And of course, we are all familiar with the passage of the seasons and how that affects the amount of radiation that we might experience, because the Earth tilts as it goes through the seasons, where in the summer months, North America has more light exposure because the northern hemisphere is pointed more at the sun, and then during the northern hemisphere's winter time, the southern hemisphere is pointed more at the sun. And so there's a variation through the year of the amount of solar radiation, both in terms of the number of daylight hours, but it's also the intensity of the light is different. So there would be a lot less evaporation during the winter time, just from the standpoint of how much energy there is to drive that evaporation. When we heat water to 100 degrees Celsius, we know that, of course, it's going to vaporize because there's enough energy to transform from the liquid phase to a gas. And what's special about 100 degrees Celsius is that the average particle has enough kinetic energy to escape into the vapor phase. But even below 100 degrees Celsius, there's still some particles that have enough energy to make it through that barrier and evaporate. It's not that there's zero evaporation below 100 Celsius and then suddenly all of the particles migrate from liquid to gas at 100 degrees Celsius. There's a continuum, is the point of variance between how much energy there is and what fraction of the particles have enough kinetic energy to vaporize. And so below 100 degrees Celsius, not all of the particles have the same kinetic energy. There's some particles that maybe are on the receiving end of multiple collisions, and they've got a lot of energy because there have been a lot of successive collisions that imparted energy to that particle, and they have enough kinetic energy to go into the gas phase. And there are other particles that are still going to be staying as a liquid because they don't have enough kinetic energy to get through that barrier. The heat that comes in from the sun is what keeps the vapor as a gas that has already evaporated. And of course, we've talked already about relative humidity and the saturation that can exist on there, how there's an upper limit of the amount of moisture that can exist as a gas. And this is just a conceptual diagram that's showing that the majority of particles in a liquid are going to have just not enough kinetic energy to go into the vapor phase, and different liquids have different vapor pressures at different temperatures. And so water boils at 100 degrees Celsius, but there are other liquids that can evaporate at lower temperatures than that. So the way that we measure the quantity of gas molecules that are above the liquid layer, sometimes we talk about that as a partial pressure. That's one way to talk about, of the molecules that are in the gas phase, some of it's nitrogen, some of it's oxygen, some of it's carbon dioxide, and some of it will be water vapor. And we could talk about the relative pressure that each of those are exerting. That's just one way of doing it. The other way, specifically if we wanted to focus on the amount of water molecules, the other way to measure how much water is in the air is the relative humidity, which is just a fraction of the amount of dissolved water molecules as a gas compared to the saturation quantity of liquid that could be evaporating based on the temperature of the air. So what causes the liquid molecules to vaporize is broadly two things. It's the energy from the sun and its transport away from this surface. Because if you have really humid air immediately above the liquid surface, then the water can't evaporate because there's no space in the air for it to move into. There has to be, you can think of it as like an open slot. So it's a two-pronged thing. There are two limiting factors, the energy delivery and also some place for the liquid water to go as it's evaporating. Over the entire Earth's surface, the average rate of evaporation is 3 millimeters per day. And of course, since the majority of the Earth's surface is water, then most of that evaporation is in open water, and the most of the evaporation will be in the equator and the central regions where there's plenty of solar radiation to drive that. Now earlier I've already referred to this phrase, the latent heat of vaporization. And that's a physical constant that describes how many joules of energy are required to take liquid water and turn it into a gas. And so here's a formula for the latent heat of vaporization. It is affected by the temperature of the water. This particular form of the equation, you'd put in the temperature of the water in Celsius, and then you'd be able to know how many joules are required to vaporize a kilogram of water. And this is one of the physical constants that goes into our empirical formula to predict how much evaporation there is. Because what we'll do is we'll estimate how much energy the sun is providing, and then compare that to how much energy is needed to do the work of taking a liquid and turn it into a gas. Here's a photo I took as I was driving one day. You're not supposed to do that, but I'm a rule breaker sometimes, especially when it comes to hydrology. You know, here's the Ohio River. This is along Route 2, headed towards Huntington. And so in the fall, you may have seen this before, where clouds and fog form above the river. And that's because the water is warm, and the moisture is evaporating from the warm water, and then as it rises, it gets to a certain elevation where the atmosphere is cool and that warm air is saturated. So it's just like a perpetual cloud over the river and just over the river in the mornings, certain fall mornings, and you can see that evaporation process occurring where liquid water is being turned into gaseous water and then, of course, condensing as a long cloud that follows the path of the river. Now, I mentioned we'd skip over a couple of the development slides that's showing the empirical equations we use to predict the rate of evaporation, and this is, I think, maybe the third slide in a chain, but here boxed in gray is the one that we actually plug numbers into. And let me talk a little bit about what this is looking at. R sub I is the radiation that's coming in, the incident radiation that would be from the sun. And then you can see this dashed arrow would be the radiation that's being reflected. And so alpha is a term that describes the reflectivity of the surface. It's called albedo. And I mentioned before that water has one kind of reflectivity, and depending on if the water has, if it's clear water, then it would be a different level of reflectivity, or if it's like murky, turbid water with a lot of suspended sediments, then it would absorb more and reflect less. R sub E is the amount of radiation that's being emitted, and how much radiation is emitted is determined by the temperature of the water. And long wave radiation is just if you've ever walked in front of a brick wall in the afternoon, like during the summertime maybe, after the sun goes down, you can walk in front of a brick wall, and even if you're not close to it, you can kind of feel the heat radiating off of that wall. And water does the same thing. It emits heat, and the radiation that's being emitted by the water isn't available to drive evaporation. What we're ultimately trying to determine is the net radiation that's available to provide the latent heat of vaporization. So this R sub n, what it's doing is it's saying, let's look at the radiation that's coming in and subtract out the component of the radiation that's being reflected, and then also subtract out the component of the radiation that is being emitted as long wave radiation. So then the net radiation, that is the difference between those, is just what's available to undergo the phase change from liquid water to gaseous water. So that's in the numerator of this formula for the radiation. So E sub R just means the evaporation rate due to the energy that's being provided. So the energy through radiation. And this evaporation rate, when we calculate it, we'd get units of meters per second. How many meters per second of water is being evaporated? In the denominator, L sub V is the latent heat of vaporization, and then we also have the density of the water as the third term in that formula. So I don't think it's necessarily important for you to memorize all of the details that leads us to this equation, but it is interesting and worth reading through the section of the book, section 7.3. And it goes through, and you probably remember from fluid mechanics when we talked about the Reynolds transport theorem and putting a control volume around an element and then keeping track of things that go in and out. So this energy balance method uses the control volume approach, and it keeps track of the mass flow of vapor. So here m dot v, that's talking about the flow of vapor, water vapor, out of a control volume. And it's simply the density of the water times the area, the surface area of the water, multiplied by the evaporation rate. And so it's the evaporation rate that we're trying to really quantify, E. So that's the energy balance method. Now, just to get some experience with the calculations and how we can estimate certain things, we have to be able to estimate, for example, the amount of radiation that's being emitted. And here's an empirical formula for that is based on the temperature of the water in the Kelvin, and then also a couple of constant, the radiation emissivity of water and what's called the Stefan-Boltzmann constant, which is a constant that has to do with long-wave outgoing solar radiation. How many watts per meter at a certain temperature is being emitted. So what we're going to do is, I just don't think we would be able to get through everything if I gave you, if we paused and I had you crunch the numbers on this. Unfortunately, I think it's better for you to understand how to apply the equations if you get the practice. But probably what we ought to do is just pull open the solutions and look at it to make sure that the approach seems logical enough. And then you will get practice on the homework assignment because there is a similar problem to this on the assignment. Let me pull open this energy method problem. So in the given problem statement, what it's telling us is that we have a scenario where there it is. Okay. We have the radiation that's coming in is 978 watts per meter squared. And then we know the temperature of the water is 26 Celsius. We've got the air temperature, relative humidity, the wind speed. And then here are the formulas and constants that we're going to use. So we kind of start at the bottom of this list. And we begin by determining how much radiation is going to be coming off of the water. Because remember, the radiation that's reflected and the radiation that's emitted is not available to drive the work that has to be done for evaporation. So to calculate the emitted radiation, we would just multiply these first couple of constants together, the emissivity, and the Stefan-Boltzmann constant, and then the temperature of the water is in Kelvin, so I had to make that conversion from 26 Celsius over to 299.15 Kelvin, which we're taking to the fourth power. And so just, scale, remember that the problem statement to begin with said that the incoming radiation is 978 watts per meter squared. Well, we're losing 451 watts per meter squared as emission. So that's the outgoing long wave radiation, and so that's not going to be evaporating water because it's emitted just based on the temperature of the water. Now we also have to subtract out the reflective effect, and so 35% of the radiation is reflected. We have this albedo defined as 0.35. And so the net radiation that's available to provide energy to drive the evaporation process is only going to be 183.9 watts per meter squared. So we've calculated the net radiation and then determined how much energy is required at this temperature of 26 Celsius. What we can calculate is that a kilogram of water needs 2.4 million joules. All right, and then for the given density of the water at a certain temperature, finally we can calculate the evaporation rate by having the net radiation in the numerator. Down in the denominator is the latent heat of vaporization, the density of the water. So it's going to be a really low rate since we have units of meters per second. But then when we multiply it by the number of seconds per day, the scale of it starts to make sense a little bit more. Remember, if the global average is about 3 millimeters per day of evaporation, here in this tropical area, this is some radiation data that was gathered in the UAE where it's pretty sunny, pretty warm, higher than average evaporation. We get 6.54 millimeters per day. So that's a reasonable number, and it just kind of is telling us if there is only one thing that's limiting evaporation, and that's how much solar radiation there is, then this is how much evaporation per day we'd see. Now, I'm sorry that we had to go through that a little bit quickly, but as far as the concept goes, does anybody have any questions about what the different aspects of the formulas are trying to estimate? So that's the energy approach. And what it assumes is that the air above the water is dry enough to accept all of the moisture that's coming out. But that may not always be true. If the relative humidity of the air above this is relatively high already, then that would reduce the actual amount of observed evaporation. So the energy equation is maybe oversimplified because it's ignoring the other important effect, and that is the aerodynamics of it. Let's see, is this full screen? All right. So consider a certain control volume that is the air above a liquid surface. And if there's radiation coming in and evaporation of the water, the air above that water has a limit to how much moisture it can hold. There's a saturation or a maximum solubility of air, of water in air. And what would drive evaporation then is the difference between how much moisture is in the air and how much can be in the air. And the closer you get to saturation, the lower the rate of evaporation would go. And this is definitely true if you've ever been into an arid region like California or Utah, Nevada. When you're out there and you sweat, it doesn't actually accumulate on your body. It's just you perspire, it evaporates into the air, and it cools you off. Whereas when you're in a place that has a lot of humidity, you sweat and then it just drips down you because it's not evaporating in the same way that it would in an arid region. And so this aerodynamic method looks at how does wind and the relative humidity affect the rate of evaporation, just in terms of how much moisture can the air actually accept. And so the variables that go into this aerodynamic method is looking at the driving force, the difference between how much moisture is in the air and how much could be in the air on a maximum. And the factors are that as you have more wind, what it's doing is it's bringing dry air down in contact with the surface of the water. So if you have less wind, by contrast, what that means is that the moisture that's evaporating isn't being transported out of the way. The moisture that evaporates from the water is staying close to the water, and there would be a boundary layer down at the interface of the air and the water that is approaching 100% humidity. Whereas if it's windy, the water evaporates and is just carried away. The other factor that this aerodynamic method looks at is large differences in temperature between the air and the water will help to increase the difference between the vapor pressure of the water in air and how much could be there when it's saturated. So looking at the effect of temperature differences and relative humidity is the other factor of just where are the spots in the air for the water to be transported to. All right, so in the aerodynamic method, there's a couple of things that we have to try and empirically estimate. And that is the saturation vapor pressure of water getting into the atmosphere. What is the vapor pressure of the water in the atmosphere currently? And down here in our formula for the evaporation rate, you'll notice that there's a difference. So on the earlier slide, it talked about a gradient as being the driving force. And the further apart the saturation vapor pressure and the ambient vapor pressure are, the greater the evaporation rate is going to be. And so what that means is just think about how the air is relatively dry in Nevada. That would mean that you have a very small E sub A. Because relative humidity is low, then the E sub A, which is the ambient vapor pressure, will be low. And a large driving force is going to increase the evaporation rate according to this aerodynamic method. The other term, B, the vapor transfer coefficient, takes into account how windy the conditions are and also the wave height. Because if there's a little bit of ripples to a water surface, it can actually have a larger surface area than if it's just glassy smooth, and if there's no wind and the wave ripples are completely still, then there's less surface area, and then that would decrease the rate of evaporation. So this ratio of Z2 to Z0, that is just looking at a certain elevation where the wind speed is being measured, and then comparing that to the average height of the water. And it's called here the water surface roughness height. And it's pretty small generally, but it can have a significant impact on the rate of evaporation. So this same example, if we look at from the perspective of the aerodynamic approach, this time remember we're not concerned with how much energy the sun is delivering. This time, by the aerodynamic method, all we're looking at is how much moisture can get into the air. Like, is there room in the air for more moisture to be evaporating? And so in this approach, we would start by estimating what is the saturation vapor pressure, what's the ambient vapor pressure, and then taking a look at the effects of the wind height and the wind speed at a certain altitude. So in this series of substitutions, you can see that although in the energy method we had to change the temperature over to Kelvin, in aerodynamic it stays as Celsius. That's just how the formula has, the empirical equations have been arranged. And so based on the air temperature, we can figure out that the saturation vapor pressure, 3893, that's just saying how much water could be in the air. And you can think of it as a partial pressure. And remember, typical atmospheric pressure is 101,000 pascals. And so this is saying that at an air temperature of 28.5 degrees Celsius, if 101,000 pascals is the overall air pressure, 3.8 kilopascals would be water. So just a small amount of the overall saturation, the overall pressure of the atmosphere is attributable to gaseous water. Now, since the relative humidity in this example is 75%, then that tells us that the ambient pressure is 2919. So there's not going to be as much of a driving force to enhance evaporation as if the gradient was larger. The other aspect here, B, is we're quantifying how many millimeters per day of evaporation there will be per unit of pressure difference that's driving the reaction. And so in the example, it said that we've measured the wind speed 2 meters above the water surface. Of course, the wind speed is going to be higher at a greater altitude, but we're going to measure what wind speed there is at 2 meters and then also take a look at the average wave height. And here it's 0.03 centimeters. And so substituting that in altogether, the aerodynamic method predicts that there's 2.18 millimeters per day. Now, remember the energy method had earlier just said that there would be 6.54. So E sub R said 6.54 millimeters per day. Whereas the aerodynamic method, E sub A, is saying that there will only be 2.18 millimeters per day. Now, the energy method was assuming that there's unlimited space in the air above the water to accept the evaporating water. The aerodynamic method is assuming that there's unlimited energy available, that the only limiting factor is how much space there is in the air above it. Now the reality is that it's going to be somewhere in between. And so there's what's called a combined method that takes into account both the effects of the energy approach and the aerodynamic approach. And it's kind of a weighted average where these weighting factors take into account something that's called the gradient of the saturated vapor pressure curve. And so you need to calculate delta based on the temperature of the air and the saturation vapor pressure. That's delta. And then this psychometric constant, excuse me, a psychometric constant for air takes into account the pressure of the air and the molecular weight of the gases. And so for air, we'll always use gamma. Our psychometric constant is 66.8 pascals per degree Celsius. So let's ignore Priestley-Taylor. It's just a similar simplification where you don't even have to calculate the aerodynamic. You just calculate only the energy method, and then it's 1.3 times this ratio. But in the combined approach, you're using both the energy and the aerodynamic estimate of how much evaporation there's going to be, and then you compute a weighted average. So remember, in this example that we calculated so far, we had 6.54 millimeters per day for the energy method and 2.18 for the aerodynamic. And if we calculate delta, the gradient of the saturated vapor pressure curve, we're putting in the calculated vapor pressure that we just already estimated, the temperature of the air, leaving it in Celsius, and get this constant 225.8 pascals per Celsius. And the combined method is essentially a weighted average, and it more heavily weights the evaporation that is predicted by the energy approach, but the overall net evaporation amount is still lower than what the energy method would predict. And so what that's telling us is that the air can't absorb as much can't absorb as much of the water as was suggested just by the energy method, that it's reduced a bit. And that's also confirmed if we apply this Priestley-Taylor approach, which is even simpler than the full combined method. The Priestley-Taylor is just saying, let's just do 1.3 times the energy, and Priestley-Taylor suggested that it would be 6.5 millimeters per day. In your assignment, I ask you to do these calculations and I give you the parameters. The tricky thing is just really keeping the units straight. And so what I'm going to do is I'm going to email you after this class the examples that I've gone through so that you've got them handy and are able to see in case you weren't able to copy it, and so that you don't have to watch the video later. I'll email you these examples that we've gone through, and that'll make it easier for you to make the substitutions. Okay, last time I went 5 minutes over, and so today we're going to quit early so you get your time back, and we will talk a little bit more about evaporation pans when we get together on Friday for class. But are there any questions about the aerodynamic method or the energy method before we close for today? Okay, so if not, remember that your next homework assignment, you've got a little more than a week, but you could get started on the evaporation calculations today, and I'll send you the notes to make that a little easier. So that's it. I'll see you on Friday.